Hi everyone, welcome to our discussion for 2271 tutorial 8. Okay, so the first question is on memory allocation, and we have a system, okay, where in the memory there are already some holes available. Okay, so holes are basically memory spaces, okay, which are empty, okay, and available for you to use. Okay, and we have them in this following order over here: 10 kilobytes, 4, 20, 18, 7, 9, 12, and 15. So here I've sort of laid out the holes. Okay, so of course in between the memory, all these colored boxes here basically show that they are occupied. Okay, so we do not know exactly what is the gap, so I just put some random blocks here to sort of signify that the spaces between these holes are actually occupied. Okay, now what we have or what is told to us is we have three processors, A, B, and C. Okay, and they would like, okay, these three uh, memory chunks to be allocated to them successfully: 12 kilobytes, 10 kilobytes, and 9 kilobytes. Okay, and we are supposed to um, describe how this allocation will take place based on these four methods over here: first fit, best fit, worst fit, and next fit. Okay, so let's look at them one by one. So for the first approach, which is the first fit, what is the approach or the strategy? We use the first hole that is available that can fit the required size. Okay, so for 12 kilobytes, okay, when I traverse through all the holes, I'll see that the first block that is big enough is this 20 kilobyte block. Okay, so from the 20 kilobyte, I'll occupy 12, okay, and 8 will be free. Okay, so that will be done. Okay, and then for the 10 kilobyte, again I start, okay, and I see that the first hole itself has 10 kilobyte of space, which is what I want. Okay, so that is also done. And for the 9 kilobyte, I will check through. So here is already full, here is only 4, then is 8 not big enough, and then I come to the next block, which is 18. Okay, so out of the 18 I can take 9, okay, and remaining will be 9. So this was also done. Okay, so for the first fit, what you basically do is you start from the beginning and then you keep going through hole by hole until you see the first hole that can fit the required size. Okay, so that's the first approach over here. Now the second approach over here is the best fit. So the best fit, what it does is it goes through all the available holes. Okay, it sort of scans through them and selects the best hole that can fit the required size. Okay, so the best hole means you want to see if you can get a perfect match. If you cannot get a perfect match, the one that is just closest, okay, to the required size. So it just so happens that for all these three sizes, 12 kilobyte, 10 kilobyte, and 9 kilobyte, we already have holes at those particular sizes. So what would happen is this algorithm would have scanned through, okay, all the holes, and then would have realized that yes, I have a 12 kilobyte hole, so this will go inside there. I have a 10 kilobyte hole, so that will go inside over here, and I have a 9 kilobyte hole, so I will allocate that for this request. So it will allocate the exact size, okay, in this case, because I have a hole that exactly matches the size that I require. Okay, so that is the best fit allocation. For the worst fit, basically what I do is I go through and select the biggest hole, okay, that can fit the required size. Okay, so for 12 kilobyte, okay, I will see that the biggest hole that can fit, okay, is the 20 kilobyte hole. So I will take 12 out of that and I will have remaining 8. So that is done. For 10, again, I will go through all the holes and I will see that the biggest hole available that can accommodate this is the 18 kilobyte hole. So I will take 10 out of it and 8 will be empty. So that is also done. And for the 9 kilobyte, again, I will go through, okay, and then I will see that I have a 15 kilobyte hole over here. So I will, out of the 15 kilobyte hole, I will take 9 and 6 will be empty. Okay, so the worst fit strategy is to take the biggest hole that I can find, okay, for the memory that I require at that time. Okay, next fit. How does next fit work? Basically what it does is it uses the next available hole that can fit the required size. Okay, so for example, okay, when I want 12 kilobyte, I will start from here, and then I'll go through, and I'll see that the first 20 kilobyte is the first one that can fit. Okay, so I would take 12 out of the 20, and remaining 8 will be empty. So that is done. And what I will do is, since I am currently at this location, I will start from the first available hole, starting from where I last used the allocation. So I'll start here. So 8 is too small. Then I'll come here. So I'll see that I have a hole of size 18, which is big enough, okay, for the size that I want, which is 10. So I will take 10 out of it, okay, and the remaining will be 8. Okay, so that will be the next one. And again, I will see, okay, so I have a hole of 8, so it's too small, hole of 7, too small, and the next one, I have a hole of 9, which is just nice what I want. Okay, so that will also be allocated. So for next fit, basically, the whole strategy is, I start from where I left off, and then I just carry on from there to look for the next available hole that can fit my required size. Okay, so you can see that the out of the 4 strategies, the best one would definitely be the best fit, because it helps to get the most closest hole that matches the requirement that you have. Okay, so it doesn't leave a lot of small empty holes in between allocated memory that eventually may never get allocated, okay, which can cause a lot of fragmentation. Okay, so that is our question 1 on memory allocation. Question 2, okay, is basically asking us to look at how, okay, the various parts of a code will be allocated to various sections in the memory. Okay, so for the first 2 variables here, integer x and integer asterisk p, both of them are global, okay, but and they are not initialized with any value. So since they are not initialized with any value, they'll go into the BSS segment. For integers f and y, they are also global, okay, but they are initialized to some value. So as long as they have been initialized, they will be allocated to the data segment. Okay, and of course, all the code that we have here will go inside the text segment. Okay, so in general, all the code, okay, that we have will go inside the text segment. Okay, now for the malloc function over here, okay, so before I come to the malloc, let's look at the g. So when I start the main, I create a variable g. Okay, so g is created, okay, so this is what we call a automatic variable, because it's created when the program starts execution. So that variable is created on the stack over here. Okay, and then I call malloc. So malloc is a dynamic memory allocation. So on the time or during runtime, where you allocate the memory, so you do not know this beforehand, correct? So for malloc, okay, you will allocate memory based on the amount of space available in the heap. Okay, so the malloc will make use of the space in the heap to allocate this amount of memory for you. Okay, next is of course we have f, but this f here is of course a global variable, so it's already been allocated, okay, from the data segment. Then you call a function sub. Okay, so when you call a function, okay, you are passing in 2 parameters to a and b. Okay, so these 2 parameters that you pass in, okay, will actually be stored on the stack. Okay, so when you call sub, you will actually be making use of the stack to pass parameters over. Okay, and inside this function sub, you create another variable called c. So that is also on the stack. Okay, so you create another entry onto the stack for this particular variable c. Okay, then of course you execute your code, and then you will return. Okay, so when you return from this function, what will happen is you will remove, or you pop all this out from the stack. Okay, and this space will become free again. Okay, so that is why we say that these are what we call automatic variables, because when you jump into the function, they are some memory space is allocated for them, but once you exit the function, you will no longer be able to access them. Okay, so if you want to still have access to them, so that is why you need to make use of this kind of approaches where you use global variables. Okay, so that is giving you some idea on how memory allocation works, okay, for a program. Now the next question is on a virtual memory. Okay. So in this question, we will consider a virtual memory system with 64 bytes per page. Okay, so within a single page, you have 64 bytes. Okay, and you have a 10-bit virtual address and a 9-bit physical address. Okay, so what is the maximum size in bytes of the virtual memory and the physical memory? So for 10 bits, I have a total of 1024 bytes of virtual memory and 512 bytes of physical memory since it's 9-bit. Okay, so what you must imagine is I have 1024 bytes over here, and I'm going to map it, okay, to within a range of 512 bytes of physical memory. So this is the virtual memory and this is the physical memory. Okay, for question 3b, they're asking us what is the maximum number of virtual pages and physical pages. Okay, so what we know is we have 64 bytes per page. Okay, 64 bytes per page. So for 64 bytes per page, I will need a total of 6 bits. Okay, to just specify the byte index. Byte index refers to what is the actual byte I'm referring to within the page. Okay, so if I look back at my allocation here, okay, so for virtual memory, okay, I'm also dividing it into pages. Okay, and my physical memory, I'm also dividing it into pages. Okay, so each of this is a page. Okay, and within this page, I have a total of 64 bytes. Okay, so to specify exactly which byte I'm referring to within the page, I need 6 bits. Okay, now what we know is for the virtual memory, I have a total of 10 bits over here. So this is 10 bits over here, and here I have 9 bits. Okay, so since I know that 6 bits is already being used for the byte offset, then whatever is remaining is what I can use for the page index. Okay, page index, okay, basically tells us which page we are referring to here. Page 0, page 1, page 2, and so on. Same thing over here, page 0, page 1, and so on. Okay, so for the virtual memory, so 10 minus 6, I have a total of 4 bits, which means I have 16 virtual pages. Okay, so I have 0 to 15 over here. For the physical memory, 9 minus 6 is 3, so 2 to the power 3 is 8 physical pages. So I have 0 to 7. Okay, so 16 virtual pages are going to map to 8 physical pages. So in terms of the address, okay, bits, this is what you will see. Okay, you will have the lower 6 bits all used for the byte index, the upper 4 bits used for this virtual page in the virtual memory, and this for the physical memory you have 3 bits. Okay, so that is how it will look like. Okay, so for the last part on this question, we are supposed to use the table here, this table, okay, to translate the following virtual addresses to physical addresses. Okay, so let's see how do we do this. Okay, so for the first example, your virtual address is 0. So virtual address 0 means all the bits are 0. Okay, if all the bits are 0, what you need to do is the same steps for all the addresses. The lower bits, which basically map to the byte offset, okay, within the page. Okay, so that number of bits in this case, which is 6 bits, will be the same. Okay, so this and this will be the same, the lower 6 bits over here. Then what you do is you look at the upper 4 bits to find out what is the page index in the virtual memory. Okay, as we just saw, since we have 4 bits for the virtual page index, we have a total of 2 to the power of 4, which is 16 entries in the page entry table here. Okay, so in this case now, what we have is we have a virtual address index here of 0. So in terms of the virtual page, I'm pointing to the entry 0. So for the entry 0, what does it tell us? It tells us that firstly, we look at the V bit, which tells us whether it is cached or not cached. So in this case, it is cached because the valid bit is set to 1. And that means that the number over here, which is the physical page number, tells me the mapping of the virtual page number to the physical page number. Okay, so in this case, we can say that the virtual page number 0 maps to the physical page number 2. So that is why I write a 2 over here. Okay, and now when I look at this as a 9-bit address, okay, it points to the physical address of 128. That means my processor will now go to the actual physical memory, okay, with the address of 128 to get the data. Okay, so that is how you translate your virtual address to physical address. Let's look at the next example, virtual address 15. So in this case, okay, what do you see? You see that the again, the lower 6 bits are the same. Okay, so these lower 6 bits are the same for the virtual address and physical address. So that part you can directly copy over. The upper 4 bits for the virtual address also point back to line 0 in the page table entry. Okay, so since the value bit is 1, 0 translates to 2 from the virtual page to the physical page. So virtual memory to the physical memory. So the value 2 is written here. And when I look at this as a 9-bit address, it points to physical address 143. Okay, so let's look at just one more example over here. For this third number here, 576, basically we see that the lower 6 bits are all 0. So we map the virtual memory address to the physical memory address, the lower 6 bits directly. And the upper 4 bits for the virtual address point to have a value of 9, which means that we look at the page table entry 9. Okay, and since the valid bit is set, okay, we look at the corresponding physical page number, which is 6. Okay, so the virtual page 9, okay, virtual memory page 9 maps to the physical memory page 6. Okay, so I write a value 6 here. And looking at the full 9-bit value here, I get a physical address of 384. That means I will go to the physical address of 384 to get the data. Okay, so that is basically how the entire concept of virtual memory and translating it to physical memory works. Okay, of course you can go through all the other examples on your own, just 2 more numbers, but it's basically the same idea. Okay, so you just look at the lower 6 bits in this case, okay, which will be exactly matching with the between the physical virtual address and the physical address, and then the mapping between physical page number virtual page number to physical page number, you need to look back at this table over here. Okay, so that basically wraps up our virtual memory question. Now the last question is on DMA. Okay, so in this question we are asked to develop a program that will move 1 megabyte of data from this address to this address. Okay, so imagine that I have a full address space here. Okay, and starting from address C0000, okay, I want to move one big chunk of memory, which is 1 megabyte, and I want to move it to this address, okay, starting from 0xD0000. Okay, so it's 1 megabyte of data. Okay, and at the same time, we want to sort of update the progress of the data transfer every 1 kilobyte of data. So every time I complete 1 kilobyte, I want to be able to update this information on some LCD panel over here. So how can we go about doing this memory move? The traditional approach, okay, which of course all of us know, is to basically simply put a loop. Okay, so this is a small I here. Okay, so to basically put a loop where you access every memory location one by one, okay, and you do a copy from the source to the destination, okay, from the source to the destination, and every time you fulfill a multiple of 1 kilobyte, okay, we update the LCD screen. So this is sort of how the pseudocode for this application would look like. The next approach that we're going to look at is basically using what we have looked at in the lecture slides, which is the DMA, the direct memory access. Okay, so basically from what you have seen in the lecture slides, you understand that a DMA helps to free up the CPU because it is a separate peripheral block within the controller that can actually take over the bus, okay, and do a memory move between 2 different locations without getting the CPU involved. Okay, so that is the main advantage of using a DMA, because it is purely a hardware driven solution, and you don't need to explicitly execute instructions to do a memory move. Okay, so in order to do it, of course, your controller itself must actually have a DMA block. Okay, and our freedom board, the Cortex M0 Plus, actually does have a DMA peripheral block within it. Okay, so yeah, of course, since the board is with you, after the module is over, you're also free to play around and try to see if you can get the DMA on your freedom board to actually work and do this kind of a memory move. Okay, so in general, what you need to do is you need to configure the DMA controllers registers. Okay, what you need to do is you need to write the start address, the destination address, as well as the number of words or bytes that you want to transfer. Okay, and what you want to do is you want to set the DMA controller to also automatically increment after each address transfer. Okay, so in this example, okay, we are going to move one chunk of data from address C000, okay, all the way to D000. And what you want is every time it moves, okay, we give the start address and address, and we say that every time you move one byte, we automatically point to the next byte. Okay, for both the source and destination, point to the next byte for source and destination. So every time you point, it does a move. Okay, and every time it completes 1 kilobytes, okay, we want it to generate an interrupt. Okay, so like most peripherals in our microcontroller, the DMA also can generate an interrupt after the transfer is complete. So what we can do in the interrupt service routine is we can use that to update the LCD and initiate the next DMA transfer. Okay, so we know that we want to move 1 megabyte, okay, but we configure it such that we do 1 kilobyte at a time, so that every time 1 kilobyte is complete, I jump to the interrupt service routine, update the LCD, and then program the DMAX registers to do the next 1 kilobyte. Okay, so that is how you can actually make use of the DMA to perform this memory move a lot more efficiently compared to just writing our normal loop to do it. Okay, so that is basically what I explained just now, the advantage of it, because it allows you to do it very efficiently. Okay, because it does not make use of the CPU to do this. Okay, it is doing it purely through a separate hardware solution. Okay, so that brings us to the end of the tutorial, and this is of course the last tutorial for the module. Okay, so I hope that you have learned, okay, quite a lot of very interesting and cool stuff, okay, through this module, not only through the freedom board and the microcontroller, but also on the RTOS aspect. Okay, so if you have any doubts, anything you want to clarify, or you have projects you're working on and you want consultation on how we can use this board or how to go about it, please feel free to contact me. I think all of you have my number, so feel free to contact me and discuss anything that you have, any ideas that you have with me. I know I'm always ready to help in whatever way I can. Okay, thank you and good luck.